started.
So chapter 18 is about, by the way, as a study strategy, you should flip through the pages of the chapter we're going to study. There are about 10 pages, I think, in this chapter. So take about 10, 15 minutes to just look through them, to train your eyes to see or recognize certain words, right? Okay, so let's start with chapter 18. It's mostly a review. Mostly a review, stuff you have seen before, probably either in a previous physics class or a chemistry class. Okay? So chapter 18 is called a macroscopic description of matter. Chapter 18. So, chapters 1 through 17, Newtonian mechanics. You studied the motion of particles themselves. You were worried about the motion of a particle and what it does, what it is in space, and so on. Now we want to study the properties of matter itself. And we're going to spend 4 chapters in thermodynamics, chapters 18, 19, 20, and 21. Okay? So it starts with section 18.1, solids, liquids, and gases. It says matter, you have different states. You got a solid, a liquid, and a gas. And then it says, how do we describe matter? There are state variables. State variables. State. Variables that describe the macroscopic, the big picture of the matter. So what would be a state variable? An example of a state variable you could think of. Yeah.
Volume.
Yeah, volume. Yeah. You got volume. Yeah. Mass.
Density.
Yeah. Density. Yeah. Mass. Density. Pressure. You got pressure.
Temperature.
Temperature. Yeah. And we will see different state variables. Another one will be entropy. Yeah, we'll talk about it. And then there is something called thermal equilibrium. So an object is in thermal equilibrium when all the state variables have a definite value. It has settled and it has a definite value. For example, if you take a cube of ice and you put it in a glass of water, does the thing that you make now, a glass of water, right? Let's say it's at 20 degrees Celsius, and a cube of ice at minus 10 degrees Celsius. As soon as you put the ice there, do they have the same temperature everywhere? No, it doesn't have the same temperature everywhere. Does it have the same density everywhere? No, the ice has different density than the water. When it melts and it settles down and everything, you give it enough time, then it would have it has reached what's called a steady state or thermal equilibrium, right? Yeah. So that's that. And then section 18.2 talks about the fact that matter is made of atoms. Yes, is made of atoms. It's not a big secret. It's matter is made of atoms. You'll study more about atoms in 231. And atoms, they have protons, neutrons, and electrons. And then there is like a bunch of terms. And I'm going to, in worksheet 1, we're going to fill out those for the class meeting here today. We're going to go through all those terms. So there are a bunch of them, so let's get them out of the way, okay? I think a lot of them are kind of redundant and maybe not even necessary, but, well, they're listed, so let's go through them. So, how many atoms would make this eraser, approximately?
Billion.
Yeah, a lot, yeah, good, that's what I wanted to hear, not a specific number, but a lot.
At least 2.
Typically 10 to the 23, 10 to the 25, 10 to the 28, it depends, right? So around somewhere there, 10 to the 20 something, right? So it's a huge number. So the number of atoms is called N, right? So here, atoms, and moles. Yeah, this thing comes on the way. So Typically, capital N is the number of atoms. So, number of atoms. How do you get this number? You get it simply by counting. Okay? So if you're able to count the atoms, you will be able to tell what N is. So it's just a number, not it's just obtained from counting. And then there is the number density. The number of atoms per unit of volume is called the number density. It doesn't have a specific symbol, but N over V is called the number density. So how many atoms per volume? So if you have a cubic meter of a solid, let's say you have a cubic meter of iron, how many atoms would there be in a cubic meter? Again, it would be a huge number. Typically like 10 to the 28, 10 to the 29, maybe 10 to the 30 would be a lot. Okay, so that's that. And then there is the atomic mass and atomic mass number. The atomic mass number is called A, and it's what you can see. So for example, in the periodic table, you have hydrogen, the atomic mass number is 1. Do they have it? Let me see here. Yeah, oxygen, it's 16. So it's the sum of the number of protons and neutrons, atomic mass number. So let me write it down. Capital A, yeah, capital A is the number of P's, protons, plus the number of neutrons, and it's given the symbol A, so atomic mass number. And then you have the atomic mass, which is the mass of one atom. And then you have the, for example, hydrogen. Hydrogen has, what does a hydrogen atom consist of? Just a proton. Just one proton, and then an electron going around. The mass is about 1.66 times 10 to the minus 27. A proton is about 1.66 times 10 to the minus 27 kilograms. That's one atom. An electron is like 9 times 10 to the minus 31. So it's even tinier. So electrons are just, you don't even add them. They just, you have to go so many significant figures to get to that. Yeah. So that is for a hydrogen atom and so on and so forth. So now, let's see. The atomic mass unit called U. So again, I'm mentioning all this. So U is the atomic mass unit, and it is equal to 1. It's called 1 U here. 1 U is 1.66 times 10 to the minus 27 kilograms, or 1.66 times 10 to the minus 24 grams, right? Okay. All right. So how many atoms? So let's say you have a mass, a sample, a piece of. Well, this is not iron, but let's say this is a piece of iron, and it has a mass capital M, and the mass per atom is little m, right? So how many atoms are there? How would you get the number of atoms?
Capital M divided by the little m.
Divided by little m, yeah. So for example here, capital M is the mass of a sample. So macroscopic, something you can hold in your hand. Little m is the mass per atom. So if I ask how many atoms are there, well, since this is the smallest unit that makes up this mass, right? So how many of them should I add? So n times this number gives me this mass, right? n times this atom gives me this mass. So capital N, the number of atoms, would be capital M divided by little m. Okay. All right, now you got moles and molar mass. Okay. What is a mole, or what is the, what's a mole and what is the molar mass? The molar mass is the mass of 1 mole of something. So what is 1 mole of something? So 1 mole of something is defined in a certain way. So let's say this is U here. So the mass of a hydrogen atom is about 1.66 times 10 to the minus 27. If I say, how many hydrogen atoms do I need to make 1 gram? So the number of hydrogen atoms needed to make 1 gram. Let's see. Let's do an example. Number of hydrogen atoms to make 1 gram. Let's see. So I want n times the mass of each hydrogen atom, right? The mass of each hydrogen atom. And I would like that to give me 1 gram, right? 1 gram. So, all right, so n times the mass of 1 hydrogen atom is about 1.66 times 10 to the minus 27. So in grams, it's 1.66 times 10 to the minus 24, right? So n times 1.66 times 10 to the minus 24 grams is equal to 1 gram. So you can cancel a gram. So capital N will be what? 1 over this number. If you have a calculator, try it. What is 1 over this number? Yeah.
1.66 times 10 to the 24.
To the minus 24.
To the, yeah, but that without the minus. Right.
Oh.
So you did the division. 1 divided by.
So the 1 over 1.66.
0.6 times 10 to the 24. Well, yeah, it should be something else. Yeah.
Okay. So do it. Try it out. So you said 0.6.
0.6 times 10 to the 24.
It's 6.02
Times 10 to the 23.
times 10 to the 23.
Yeah.
All right. So if you have a calculator, try it out. And this is called, this number has a special name called Avogadro's number. It's a mole. A mole of something is this much of that something. Okay? So like a dozen of eggs is 12 eggs, right? A mole of eggs is this number of eggs. Some 6 times 10 to the 23, right? Of eggs. So this is called Avogadro's number here. And A is 6.02 times 10 to the 23 per mole. 23 of that thing for every mole. So mole to the minus 1 per mole. And then there's, yeah, again, it keeps, the terminology keeps coming. So the number of moles is given the symbol little n. So let's say I have 3 moles of something. 3 moles of something means multiply this number by 3, right? Yeah, because 1 mole of something is 6, let's say it's 6 times 10 to the 23. 3 moles of that thing will be 3 times the number of moles. So 3 times 1 mole. So it'll be 18 times 10 to the 23, right? So little n is the number of moles. So that's why I said let's just get it out of the way. Yeah. So number of moles, n is the number of moles. So if I say 3 dozens, how many eggs is that? 36. 3 dozens. Yeah.
Sorry to ask, but where does the atomic mass unit number come from again?
The atomic mass. This one?
Yeah.
So basically the mass of one proton, or the
Oh,
mass of a
okay.
hydrogen atom. Yeah,
Thank you.
yeah, you're welcome. I mean, there, you can read about it, it's in the book, it's exactly defined as like the mass of one carbon, a carbon atom is 12 units of those. It's in ratio to it. But just take it as the mass of a hydrogen atom. That's good. Yeah.
Thank you.
Yeah, you're welcome. Oh, I'm writing like this. Okay. Number of moles is little n, right? Little n is the number of moles. And then there is something called the molar mass. Okay, molar mass. Mole. What is molar mass? What do you think it means?
Mass per mole.
Yeah, yeah. Take a mole of something and then figure out what the mass is. So what's the molar mass of hydrogen then? 1 gram. Yeah, 1 gram. Because again, the number of moles was defined as the 1 over the mass of a hydrogen, right, in grams. So 1 mole of hydrogen would weigh 1 gram. Yeah. 1 mole of carbon would weigh 12. 1 mole of oxygen would weigh about 16. All those numbers there. Nitrogen would weigh about 14. And when I say oxygen, I mean oxygen atoms. Because when you say, we will get an example with an oxygen molecule. It usually comes in O2, right? So it's 2 oxygens put together. So if a mole of O2 will weigh how many grams?
32.
32, yeah. Twice of 16, 32. All right. So, and I have some examples in the homework and also in the worksheet. So we can go over those. And I would do, I think, an example here. Let's look at example 18.2. Page 510. So it says here, all right, well, here it is. 100 grams of oxygen gas, so it's O2. 100 grams of oxygen gas is how many moles of oxygen? So let's see. So example. How many moles? How many moles of O2 are in 100 grams of O2? Basically, that's the question. So, an oxygen by itself, right? An oxygen atom by itself will weigh, an oxygen atom by itself will weigh 16, a mole of oxygen atoms by themselves will weigh 16 grams, right? So, a mole of O2 will weigh how many grams?
32.
32, yeah. A mole of O2 will weigh 32, right? Yeah. So, 1 mole of O2 has a mass, of 32 grams, right? Has a mass of 32 grams. So 2 moles of O2 will give me 64 grams. 3 moles of O2 will give me how many grams? 90. Right? 1 mole gives me 32 grams. 2 moles give me 64. 3 moles give me 96. So it's about 3 moles to give me 100 grams. So what should I do to get the exact number?
Divide by 32.
Yeah, 100 over 32. So the number of moles, N is the number of moles, would be the mass of the sample that you have divided by the molar mass, right? By the molar mass. And the mass of the sample we have here is 100 grams, and then the molar mass is 32 grams. So you get 3 something. $3.13. I mean, this one is 32 grams per mole, so it flips because of that. Okay. another way to do it, but this is it.
And
Any questions so far?
what is the other one?
Oh yeah, so you say an oxygen atom has the mass of 32 hydrogens. I'm sorry, an oxygen molecule would have the mass of equal to 32 hydrogens, right? So 32 times this U. 32 times this. That's the mass of each oxygen molecule. So then you multiply that by by N and figure out what N is to make 100 grams. And then you can figure out what the number of moles is. Okay. Nick?
Oh, no.
Okay. So by the way, feel free to stop me. I'm willing to go back and talk about things. That's good. You still have some time. Maybe there is a good chance we finish this chapter today. That'll be good. I just need to get rid of this chapter, get it out of the way. And then, the fun stuff begins next chapter and the following one. The real fun stuff is electricity and magnetism, I think. Then temperature scales. So how do we measure temperature? What's the temperature outside right now? Does anybody know approximately?
70 degrees.
Yeah, about 60 degrees, right? So at first you can have the notion of temperature, right? You get hot and cold and then moderate. That's not good enough, right? That's not too accurate. And then people came up with different scales. So anything that changes its property when temperature changes, when it gets hotter or colder, can be used as a thermometer. So, for example, not very accurate, this pen, if you heat it, it expands. I mean, obviously not until it melts. But if you heat it, it expands. If you cool it, it shrinks. But it doesn't shrink or expand appreciably that you can even notice. But in principle, if you have something accurate enough to measure the expansion, you can kind of calibrate it and figure out what the temperature is. So what people do is you have let's say the Celsius scale, so temperature scale. You got the Celsius, I think that's how it's spelled, degrees Celsius. It's based on water. So water freezes at 0 degrees Celsius, right? And then it boils at 100. So you take, let's say, let's say I take this pan, assume the pan kind of shrinks and elongates appreciably. I put it in water at 0 degrees, at freezing water, 0 degrees, and I measure the length. And then I heat it until to boiling water, assuming this doesn't melt. It's plastic, so it probably would melt. But assume it doesn't. It gets longer. So then I can calibrate. I say the length was, let's say, 5 centimeters at 0 degrees. And then at 100 degrees, it became 10 centimeters. So it expanded by 5 centimeters over 100 degrees range, right? So I can calibrate it and say 5 centimeters over 100 degrees. So for every degree, it will expand by a certain length. But there is one assumption we're making. We're assuming it expands linearly, right? Because if this is the temperature, and this is the length, let's say this is the 0 degrees Celsius, and this is 100. Let's say at 0 degrees, this is the length, and at 100, this is the length. You went from here to here, right? We just assume it goes linearly, and it's approximately linear. I mean, obviously, it could do this, or it could do that, right? It could be nonlinear, but we will just assume it's linear. Okay? So, again, degrees Celsius is based on what? Water freezes at 0, and it boils at 100. And then there is the Fahrenheit scale. We'll get to linear expansion in a little bit. Fahrenheit, degrees Fahrenheit, right? Where is it at? Yeah, something, yeah. And it's, they're related to each other. It's a weird scale. Water freezes at 32, right, Fahrenheit? And it boils at 212. And so there is a relationship between the two scales. If both of them are linearly related, you can use the 2 points where they agree, that you have. 0 is 32 in the Fahrenheit scale, 0 degrees Celsius is 32 in the Fahrenheit scale, and 100 degrees Celsius is, I think, 212, right, the boiling temperature?
Yeah.
I think it's 212, yeah. And so you use these 2 points, right? If you have an X and Y relationship, if you have 2 points, you can figure out the equation of the line. And the equation turns out to be F, or let me write it this way. The temperature in Fahrenheit is 5/9 the temperature in degrees Celsius plus 32. Plus 30. Okay. Yeah, so there is it. Any questions on this one? Seems reasonable. Okay. So, and then there is the Kelvin scale, or the absolute scale, Kelvin. It's K. And it's related to the Celsius scale by the following: T in Kelvin is equal to the temperature in degrees Celsius plus 273. 0.15. 273 plus 273. Yeah.
Wait, isn't Fahrenheit 9/5?
Yeah, 9/, oh yeah. It's bigger. Yeah, 9/5 plus 30. Thank you. You know what? Let's get this one. Let's do an example. Yeah, let's do an example. So the temperature in Fahrenheit, so here is 0 degrees Celsius, right, is the same as 32 Fahrenheit, right? This is F, and this is C, right? Temperature is C. And 100 is 212, right? 212. 212. And I want to get a relationship between the two scales. Okay? I want to get a relationship between the two scales. So here is C, and here is F, right? And 0 is 32, and 100 is 212. So 100, 0, 32, 2, 1, 2. And I want to get the equation of this line. How would I do that? First, you get the slope, right? For any line, I want to get a relation like this. F is equal to some number, some slope. Let me call it M times C plus B, right? Slope plus the y-intercept. The y-intercept is clearly 32 from the picture. What is the, yeah, so the y-intercept is 32, so I get this. MC plus 32. Now what's the slope? The slope is the rise over the run. So what's the rise? The rise is 212 minus 32, right? Little m is 212 minus 32 over the run, which is 100. And 212 minus 32 is what? 180, thank you. Over 100. Over 100. So that's 18 over 10, or 9 over 5, right? So this one. And for Kelvin, you just add 273 to the Celsius, right? So when it's 0, the freezing point of water, 0 degrees Celsius, would be 273 K, right? 273 K. The significance of the temperature in Kelvin is all gases, their pressure will go to zero when you cool them down to 0K. Pressure, yeah.
Is there a significance for Fahrenheit?
There is a historic reason that I read a while ago, and I forgot now what it is. It's on Wikipedia. Go ahead and read it. Yeah, yeah. I forgot what the 32 and 212 were, but it's probably some in a particular country, from what I remember, and they are above sea level or below sea level, something like that. So yeah, there is a reason, and you can come up with your scale, right? I think in the book, in the homework, there is an example or a problem like that. A different scale called the Z scale or something, where water boils, let's say at whatever, at 500, and it freezes at -50, right? Some weird scale. And then what's the relationship between them? It's exactly like this. You find the y-intercept and you find the slope, and you get the relationship between them. Just keep on going. Thermal expansion. Thermal expansion. So things, again, if you heat them, they expand. They expand. If something has a length, then you will notice the length get bigger. If it's a volume, you will notice the volume get bigger. And the amount of extra length will be this. So linear expansion. Let's do that. Or thermal expansion first. Thermal expansion. Thermal, something with temperature, right? So let's say I have a rod that has an original length L, right? A temperature T initial. The temperature now is T initial, or T1. And then I heat it up. I bring like put it on a burner or something, heat it up. When you heat it, usually it expands. And the amount by which it expands is called delta L. If you cool it, it will shrink. Right? If you started at this temperature here, if you started with this and then you cooled it down to this temperature, it should come back here. It should shrink. So it can shrink or expand or shrink. So delta L, let's just see what it would depend on. So what do you think it depends on?
Material.
The material itself. And the material itself is, you got alpha. It's called the coefficient of linear expansion. And so coefficient of linear expansion. We'll get the units of it in a moment. What else would it depend on? I mean, if I heat it by 1 degree versus 10 degrees versus 20, which one will expand more? The change in temperature. The larger the change, the more the expansion, right? So it's proportional to the change in temperature, delta T. And then if I heat a 1 meter rod versus a 10 meter rod, which one will have the larger expansion?
The 1 meter.
Which one will expand by more? The longer one, yeah, the 10 meter, yeah. In fact, it will expand 10 times more. Because if 1 meter expands by 1 centimeter, and the next meter expands also by 1 centimeter, and the next meter expands by 1 centimeter, and so on. So it's proportional to the length, yeah. So L, the original length, yeah. And so that's called the coefficient of, or this is called the thermal expansion. This one is linear expansion. Linear expansion. And alpha here, let's think about what the units would be. Delta L will have what units?
Millimeter?
Of length, right, or meters, yeah. And L already has units of meters. So this is meters, this is meters. The meters cancel. The left side will be a dimensionless quantity, right, if we cancel the L. That means alpha and delta T, they have to have opposite units, inverse units. So delta T is in degrees Celsius, then alpha would be 1 over degrees Celsius. 1 over degrees Celsius. By the way, delta T here, it doesn't matter whether you measure T in Kelvin or degrees Celsius. Why?
Related, there's just a difference of 270.
Yeah, they're just differ by 270. So it doesn't matter if you convert it to Kelvin and then take the difference between them, the 273 that you added will cancel anyways. Yeah, so a change of 1 degree Celsius is the same as a change of 1 Kelvin. It's the same change. Right? If you step up by 1 degree Celsius, it means you have increased the Kelvin by what? By 1 Kelvin. Is that okay? Yeah. Okay. So let's do an example here. It says you got a 55 meter. It's example 18.3. Yeah, I still have some time. So example 18.3 from the book. And so suppose you have a pipe. It's very long. And they try to make it practical here. It's a steel pipe and it runs in a refinery. And the refinery can, oil can flow in, or gas or something, or oil, I think. And so the pipe is 55 meters long, so 55 meters long. L is 55 meters, and the temperature T initial is 5 degrees Celsius. The question is, if you run oil through it, and the oil happens to be of a temperature of 155 degrees Celsius, so let's say now the temperature increases to 155 degrees Celsius, the question is, what is delta L? What's delta L? What do I need to give you to do this alpha? I need to give you alpha. So alpha for steel, this pipe is made of steel. I think I mentioned that. Alpha for steel, you go to the book and it's there is a table, or you use Google and then find it. In a test or a quiz, it's given to you. You will be given. Of course, nobody goes and memorizes tables. Not reasonable. Yeah. So steel has an alpha of 1.1 times 10 to the minus 5. So let me write it. 1.1 times 10 to the minus 5 per degree Celsius. That's alpha. So we can easily find delta L by just this formula. So delta L is alpha, which is 1.1 times 10 to the minus 5, right? Times the length, the original length, which is 55 meters. And then the change in temperature. Yeah, 155 minus 5, I'll write it. So yeah, that's 155 minus 5. And if you do this,